Okay, so in the last video, we talked about three different atomizers, and we ended talking about the ICP torch. We said it could achieve very, very high temperatures, and you would want to use the ICP torch. In fact, it would be a preferred method of atomization for atomic emission spectroscopy, but not so much for absorption spectroscopy. So why is that? Let's dive into that. The reason why, ultimately, is that temperature will affect the population of atoms in different states in the air atom. And what I mean by that is at low temperatures, so essentially I'm going to summarize for you, okay? At low temperatures, our ground state of our atom, ground electronic state, will be more populated. But as the temperature gets higher and higher and higher and higher, heat can actually be absorbed by the atoms and used to electronically excite atoms. In other words, we're using the high temperature environment to bridge the energy gap between the ground state and excited state. And we're taking atoms and we're populating them into the excited state. We're transitioning them into the excited state at high temperatures. Now, if we do that, think about it. Don't we then by default reduce the number of atoms in the ground state? So if I'm trying to do, let's say 3s to 3p transition in our sodium atom, that's absorption, going from the lower to the high. To carry out that absorption, well, I want to have a lot of atoms down here, don't I? In the 3s, because the more atoms I have in that 3s state, the more chance that I can get absorption to occur and absorption signal register. But if I heat the atoms too much and I promote them up into the 3p just by the heat energy, that's a bit of a problem for my absorption, isn't it? They're already in the 3p. They can't absorb that color of light that I'm trying to get them to absorb, and I'm not going to get a signal. So depopulation of my ground state for absorption spectroscopy can be a bad thing. But might it be a good thing for emission spectroscopy? Think about it. If I can populate atoms up into the 3p, the excited state, they're probably going to drop back down to my ground state, aren't they? And in the process, they will emit light of their characteristic frequency. So this fact that temperature can affect the population of atoms in given electronic states is really, really important. And this idea that the heat in our atomizer will initially be used to atomize our material, but after that, it just goes into electronic excitation. So if we make our atomizer too hot, it can actually hurt our absorption signal. However, for emission experiments, you would want to make the atomizer as hot as humanly possible. And that's why the plasma is great for emission experiments, really the preferred method for atomic emission. However, the plasma might just be a bit too hot for atomic absorption, okay? Now, to understand why this is mathematically, we can actually look at this equation, which is the equation for something called the Boltzmann distribution. It's basically an equation which helps us compute this ratio over here on the far left, which is a ratio of populations of states, okay? Now, I is characteristic of our excited state. So over here on the left, what I'm basically doing is I'm computing the ratio of atoms in the excited state to atoms in the ground state, or really any lower lying energy level, okay? Now, what is that equal to? Well, it's equal to a number of things multiplied together. And then the first is this ratio right here, the ratio of the p's, okay? Now, what in the world are these p terms? They're actually kind of the hardest to sometimes figure out, okay? But they're basically determined by the number of degenerate states for both the excited and the ground state. Degenerate meaning equal energy, okay? So that ratio is actually fixed for a particular transition under study. There's not really much that we can do to change that. But the second part of the equation is the one that we really want to key in on. This is E, the base for natural logarithms, raised to the power negative delta E divided by KB times T. Take a look at this. There's three variables. I mean, the E is just the base for natural logarithms. It's a number, right? The delta E is the energy difference between the two states, the gap in energy between the ground and the excited states. That's our delta E. KB is just our Boltzmann's constant. It should be a subscript, okay? It's equal to this number, has a value of 1.28 times 10 to the minus 23rd joule per Kelvin. Don't forget the negative subscript there. So it's a small, tiny number, right? It's our Boltzmann constant. It's always that number. And T is a bit of the superstar of this equation because that is our Kelvin temperature. So what this equation allows us to do is to predict the ratio of atoms in the excited state compared to the ground state as a function of temperature and delta E, the energy gap between the states. Now, for any excited state and ground state combination, there is, of course, a delta E, a gap in energy between them. And that number should go right here in joules. Now, the bigger that gets, the numerator of that fraction increases and increases and increases, doesn't it? So the fraction, once I compute it, the whole thing, right? Once I compute that whole thing and I raise it e to the negative power, it seems like that makes that term smaller and smaller and smaller, doesn't it, mathematically? So as delta E gets bigger, the energy gap gets bigger, the resultant product of E raised to the negative delta E or KBT gets smaller and smaller and smaller. So functionally, what that means is if my energy gap between my ground and electronically excited state gets bigger, at any given temperature, the fraction of atoms in the excited state compared to the ground state will get smaller and smaller and smaller. It makes sense, right? As delta E gets big, it's going to be harder and harder and harder to populate my excited state. So most of my atoms are just going to be in the ground state. Now, what about the effect of temperature, T? That's Kelvin temperature, don't forget. Now, for our Kelvin temperature, T, let's see, if that gets bigger and bigger and bigger, right? We're talking about that term right there. Getting bigger and bigger and bigger, that fraction for any particular delta E would then get smaller. So I would take E and raise it to a negative power of a smaller and smaller and smaller number. And in doing that, I actually have the opposite effect. As the temperature increases, the ratio also increases. When I say the ratio, I'm talking about this, right? So as the temperature increases, the Ni over Nj increases, the atoms of the fraction of atoms in the excited state increases. We're populating our excited state more and more and more at higher temperatures, and this equation just mathematically formalizes that for us, okay? So I'm sorry for there's some weird typographical errors down here, but I wanted to do just a quick comparison of numbers for our 3S to 3P transition for sodium for 589 nanometers. So this wavelength, I can convert that to an energy gap between the higher and lower state. And if I do, it's 3.37 times 10 to the minus 19th joules. So I would take that and plug it into my equation for my delta E, plug my KB in, and now I can do comparisons of what this ratio might be at different temperatures. So that's actually kind of what I tried to do here. So the first sort of back of the envelope calculation I did was what that ratio might be at room temperature, RT. And what I got was 5.8 times 10 to the minus 42nd for my Ni over Mj. And remember what that is. It's the fraction of atoms in the excited state referenced back to the ground state. So what that says is, gosh, I got to look through a lot of atoms before I even find one in the excited state, right? Overwhelmingly, our atoms reside in the ground state, all right? That's an overwhelming fraction in the ground state. And that's at room temperature, right? 25 Celsius. Now, what if I increase to 5,000 Kelvin? This is quite quite warm. Well, if I do the calculation for 5,000 Kelvin, I get a different story. I get 0.0158 as my ratio, Ni to Nj. So at 5,000, gosh, just about 1.5, 1.6% of Nj is Ni, which means, okay, so 1.6% excited state reference back to the ground state. That's a much higher number. And that might seem like just a small fraction. I mean, most of the atoms are still in the ground state, right? But gosh, that's much bigger than 5.8 times 10 to the minus 42nd. So by increasing my temperature to 5,000, I've really affected the number of atoms in my excited state. Just thermally, I've populated that. And this equation allows me to formalize that in a quantitative way. Okay, it's the Boltzmann distribution, basically. And we can use that to explain why atomic emission spectroscopy is great at highest temperature as possible. But absorption spectroscopy, the general rule for absorption spectroscopy is you want to make the temperature warm enough to completely atomize your sample, but no warmer. And that's it, okay? So at low temperatures, room temperatures we might say, the overwhelming majority of atoms are in our ground state, our lowest energy state they can possibly be in. And as the temperature increases, we start to populate higher energy states. These little dots represent the population of the higher energy states. We start to depopulate the ground state, and other states kind of have a fighting chance at higher temperatures because we can bridge that delta E energy gap with thermal energy, basically, okay? And that's kind of all we need to know about this. Okay, so important principles for atomic absorption, AA, and AE, atomic emission work. You want that ratio to be large if we're doing an atomic emission, because the larger that ratio, it means you're populating your excited state. You're going to get a brighter and brighter emission. We do that by high temperatures. For atomic absorption, you want that ratio to be small. Now you might say, oh, low temperatures, right? But remember, you have to atomize your material. You have to atomize your material. So in atomic absorption, the temperature's got to be high enough to atomize the sample, to break molecules down to atoms. You got to do that, okay? But no higher. But in emission experiments, make that flame as hot as you possibly can. That's always advantageous to you, okay? All right, so nonetheless, these are some important principles to think about. Now, the last remaining topic that I want to address this chapter is return to line widths for atomic spectroscopy. Earlier, we decided that if you plotted out the power of emission or absorption versus wavelength, that atomic spectral lines had some width to them, but we learned that the half width or the full width and half height, something on the order of 0.01 nanometers. Very narrow lines. But we didn't explain at that time why we don't see an infinitely narrow line. I mean, think about it, right? There's an allowed electronic state here. Maybe that's your 3p again, and then there's this 3s in sodium. It has a different precise energy, and the gap between these two is a very precise number. It's exact, right? No edging. So why then do we even get this narrow line feature of 0.01? I mean, why isn't this spectral feature infinitely narrow, right? Why not? Well, the reason why is because atomic spectral lines can be broadened or widened due to a couple features. Let's talk about those real quick. The two features that we're going to consider are something called Doppler broadening, and then we'll consider pressure broadening. Doppler broadening is based on the Doppler effect. And the equations over here on the right, I'm probably not going to ask you to use these for an exam or anything like that. I just kind of included them in the slide. So you don't have to necessarily know these equations, and you don't have to put them on your index card. But what they do for us basically is describe the extent of Doppler broadening in frequency space and also in wavelength space. And there's an equation You can figure that out. And it's actually really simple. M is the molar mass, and T is the Kelvin temperature, and you just multiply it by this number, and you can get the extent of broadening. But again, we don't necessarily need to do that mathematically for our exam. But what I would like you to know for the exam is just a physical basis for this form of broadening, Doppler broadening. And again, it's caused by the Doppler effect. Now, the way I usually explain this to people is think about an experience in your life when you were driving in a car and you were driving past an oncoming vehicle or train or something of the sort that had its horn blowing. Okay, what did you experience? Well, I'll tell you kind of a story from my life. I used to live in the state of Nebraska. And trains are real big in Nebraska, as it turns out. They haul a lot of coal from Wyoming back east for power plants. Huge amounts of coal. And every day in the town where I lived, there was, gosh, probably 50 trains, each about a mile long, carrying coal back east from Wyoming. And oftentimes, just the way that Nebraska is laid out, the railroad played a big role in the development of the state. And a lot of the small towns will basically be along the rail route. There's not much in between, and they built the highways between towns, essentially parallel to the rail route. So when you go driving from place to place, it's not uncommon to drive right next to the train tracks, and you pass these trains. So, I can remember times when I'm driving towards a train, I can see it coming, and it starts to blow its horn, right? Everyone's familiar with the train horn, really loud. So what do you hear as you drive past it? Well, you'd hear something like this. Something like that, right? And I think you're all familiar with this just from your own experience. And this is an example of the Doppler effect. The train's horn has a very specific frequency, and it doesn't change, right? It's the same frequency all the time, unless the horn breaks or something, but we'll assume that doesn't happen. So it's always the same frequency. But when I experience that driving in my car past the horn's engine, I hear something very different, right? When I'm driving towards the train and approaching the train at my velocity and its velocity relative to one another, I hear a higher pitch or higher frequency horn. And then once we pass each other, I hear a very different sound. That higher frequency quickly fades to a lower frequency, higher frequency to lower. Now, the train's true horn sound didn't change at all. It's just the way I experience it, right? Because me driving in my car, 65 miles an hour, because of never speed, right? I'm moving towards and then away from the train's horn. And when I do that, I experience experientially a slight shift in the frequency of the sound that I hear. And when I'm driving towards the horn, towards the source of the sound, the frequency will be higher because my velocity basically draws me towards it. You can think of it that way, right? And when I pass the horn, the sound's going to be a larger frequency than true because I'm driving it away from it, right? And I'm gaining ground on the sound wave, if you want to think about it that way. This is the Doppler effect. Now, atoms in these flames, really whatever atomizer, can experience a very simpler Doppler effect that causes the line width of their emission and absorption to broaden. And the reason why is more or less just like what we experience with the train. Over here, we might have our hollow cathode lamp producing light. Light's a wave, right? And in the flame, we've got an atom. Now, that atom is basically in random motion, bumping into other things, right? But at any given point in time, it's going to have a net velocity vector, either left or right, okay? So there'll be some velocity vector either towards the source or maybe a different atom has a velocity vector in that dimension away from the source. But every atom will have a certain velocity vector either towards or away from the hollow cathode lamp source, which is producing these waves of electromagnetic radiation. Now, because of that, they're not that unlike you driving in a car towards the train, are they? They may experience, if they move very quickly, which they do at a high temperature environment, they may experience a slight Doppler shift relative to that beam of light and its wave-like properties. And as a result, the spectral features can be broadened. The atom which is moving closer might experience a slightly higher frequency, in a way it's slightly lower. And their absorption and emission frequencies will be adjusted as such in accordance with these equations. Okay, so more or less, this is Doppler broadening. And Doppler broadening is in high temperature environments is very often the major source of broadening. And because of this Doppler broadening, the line widths are broadened 100-fold compared to their natural line widths, which is very significant. Now the spectral lines are still very, very narrow, okay? Maybe 0.01 nanometers in width, but that's much broader than what they would be without Doppler broadening. So oftentimes a major source of broadening. It's kind of interesting, okay? The other source of broadening is called pressure broadening. Now, if we take our atoms and we put them in an environment of basically anything other than a vacuum, okay? So we surround them with other atoms in the gas phase. It's essentially increasing the partial pressure of everything else. This effect will cause broadening of spectral lines. The reason behind this is it's believed that collisions between the atoms or ions in the environment which you place them can cause ever so slight distortions of the atom or ion's energy levels, ever so slight, very, very small, very fleeting during one of these collision events. But nonetheless, because the electron distribution or the energy levels around the atom is ever so slightly distorted, this will lead to line broadening because the energy gap between our two states will also be ever so slightly distorted or changed, modified. Ever so slight broadening of our spectral line results. This is referred to as pressure broadening. I think with that, we've kind of done our due diligence here for this chapter. So I want you to know, and you can read through it in your book and learn lots more. There's lots more to learn, there always is, right? Read through it in your book. I want you to know the 3 kinds of atomizers. You know the flame is the most common. There are some of the working principles of both atomic absorption and atomic emission. Know the block diagrams for all the instruments. That tends to be important here in the second half of the class. Know how to label them, know what each part does, how one of these devices are basically put together, how hollow cathode lamp works, be able to explain that, know the block diagrams. You know, that's what really I'm hoping that you get an overview of here in these chapters, okay? So I hope you enjoyed atomic spectroscopy. Remember, about 75% of the elements on the periodic table can be measured pretty easily with this technique. It's pretty selective, reasonably sensitive. It's really kind of a great technique and very interesting analytic